All right, we're going to look at rates of change. A rate of change is a comparison of how two variables change in relation to each other. So it's going to be two different variables, two different quantities involved. In particular, it's a ratio means divide, of how much the output values change for a given change in the input variable. So the units of a rate of change might be quantities such as miles per hour, pounds per square inch, dollars per cubic yard, etc. The units will be the output units per the input units. For example, an avid bird watcher has recorded the number of different species of birds observed in his backyard for several months. So they've got the months and the number of birds. Month 1 would be January, 41 species. Month 2, February, would be 43 species. March is month 3, 65 species, etc. Between January and March, months 1 and 3, the number of species increased by 24 birds in 2 months. So between 41 birds to 65 birds is an increase of 24 birds, and that was an increase of 2 months. The rate of change for that interval would be the 24 birds over a span of 2 months, which gives us 12 birds per month. Well, between April and June, months 4 and 6, the number of bird species decreased by 12 birds. Going back to our table, April would be month 4, June would be month 6, and we can see the number of species decrease from 54 birds to 42 birds, so a decrease of 12 birds over that 2-month period. So the rate of change for that time interval would be a negative 12 birds, again over a 2-month span. Gives us a rate of change of negative 6 birds per month. So again, the units on a rate of change are 1 unit per another unit. The units for the dependent variable, the output, which is the number of birds, per the units for the input variable, which in our case is months. To define rate of change, or average rate of change, we've got several different notations that all mean the same thing, and you can kind of decide what's your favorite form of the notation. In words, the average rate of change is the total change in the output variables divided by the change in the input values. So that's a word way to say it. I'm a mathematician, so I like things a little more symbolic. So another way of thinking of average rate of change is the change in the output values divided by the change in the input values. Now, if you want to go more symbolic than that, another way a shorthand that mathematicians commonly use for change is change delta, the little triangles of Greek letter delta, and we use it to symbolize change, the change in the output variables. Now, the output variables we commonly refer to as being the y variables, the variables along the vertical axes. So change in y per a change in the input variables. And the input variables we often refer to as being the x values, the values along the horizontal axes. And then the third way to talk about average rate of change would be the difference in two y values, y2 subtract y1, divided by the change in the input variables, the change in the x values, x2 subtract x1. Now, if that's starting to look familiar, you probably remember the formula for the slope of a straight line. A straight line has a rate of change that's consistent all along its length. But we can talk about average rate of change for functions that are not straight lines. That's what we're looking at here, where the average rate of change can vary. So in particular here, we've got a quadratic function. The average rate of change on the interval from -3 to 0. We can find it by first looking for the output values on the graph. So on the interval from -3 to 0, so we're looking at where x is -3, and where x is -3, we have a y value of 10, and where x is 0, we have a y value of 1. So to write that in function notation, when x equals -3, the output value of the function at -3 is 10. And when x is equal to 0, the output value at 0, the value of the function at 0, is 1. So if we want to find the average rate of change, we can look at the rate of change in the y's divided by the rate of change in the x's. And it is important to be consistent. Since I'm using my second point, my ending value, my interval first, and my beginning value, my interval second. So I've got the -3 and the 10 coming second in my formula, and my 0, my input is 0, my output of 1 coming first. As long as we're consistent, we shouldn't have any trouble. 1 subtract 10 would be -9. 0 subtract -3 would be 0 plus 3, so that'd be +3, giving us an average rate of change of -3. Now if we look at our 2 points here, and let's draw a line. This is what we call a secant line when you get to calculus. I didn't draw it terribly straight, but I think if you look at use your imagination a little bit, we can see we've got a slope down 3 over 1, down 3 over 1, down 3 over 1, the average slope between those 2 points. And again, this is going to come up in calculus, but that's what we're finding when we're finding the average rate of change, the rate of change between those 2 points on average. Okay, we don't necessarily need to look at a graph to find an average rate of change. If we've got the function, we can do the calculation. So if we have g of x equals 3 over x plus x on the interval from 1 to 3, we'll first need to calculate the output values. So when x equals 1, g of 1 would be 3 divided by 1 plus 1, replacing the x with the values of 1. That gives me 3 plus 1 equals 4 for the output value when x is 1 for the input value. Then if the other end of our interval is x equals 3, g of 3 is 3 divided by x, so 3 divided by 3, x being replaced by the 3, plus x, so plus another 3. That gives me 1 plus 3, which is also 4. Then my average rate of change y2 subtract y1 over x2 subtract x1. This will be 4 subtract 4 over 3 subtract 1, which gives me 0 over 2. Nothing divided by 2 is nothing. So I'm getting an average rate of change of 0, which is a little surprising. So to double check myself, because sometimes I make mistakes, I'm going to take a look at the graph. Okay, So my function here is graphed, and I was looking at the interval from x equals 1 to x equals 3. So x equals 1, I've got a y output of 4, and at x equals 3, I've got a y output of 3. So my secant line through those 2 points, you can see, has a slope of 0. So even if a graph's not given, I like to go ahead and do a graph just to make sure my average rate of change seems reasonable after I've calculated it. Okay, so some vocabulary that'll come in handy in this class and the next class after this. Functions, I don't think they're going to have too much trouble with this. It's pretty intuitive, even if it seems like a lot of vocabulary. Functions increasing on the interval if the outputs increase as the inputs increase. So visually, that means the graph goes uphill as you look at it from left to right. So on the function here, as we look at it from, starting on this interval, as we look at it from left to right, here the function is increasing as we go along the interval. As long as the function is increasing, you can expect the average rate of the change will be positive on that interval. A function is decreasing on an interval if the outputs decrease as the inputs increase. That means the function goes downhill along that part of the function. If the function is decreasing on the interval, you can expect the average rate of change will be negative on that interval. And then a couple other definitions that will come up now and then. There. Where you can see it. The point where a function changes from increasing to decreasing is called a local maximum. So, get this up here a little higher. So if we have a function that is first increasing and then goes from increasing to decreasing, the point where that change occurs is called a local maximum. A point where a function changes from decreasing, so we were decreasing here, it changes from decreasing to increasing, so we were increasing in here, that point is called a local minimum. And again, I think as long as you're looking at the graph, you won't have any trouble remembering those definitions. They're pretty intuitive. So one more topic, again, with some more definitions, and this one might be new to you. It's called concavity. Have you ever heard on a newscast the rate of unemployment is increasing at a decreasing rate? What exactly does that mean? We're talking about rates of change, but we're using both increasing and decreasing. So if a rate of unemployment is increasing, that means the average rate of change is positive. So if we're, there we go. So if it's increasing, the average rate of change is positive, the graph's going uphill. But if those average rates are increasing at a decreasing rate, the average rate, as we move along the interval, is getting smaller, but staying positive. The steps up the hill are getting less steep as we go up. And again, most of us are visual, so we like to look at things. Let's take a look at a couple graphs here. So we say a function is concave up if the rate of change is increasing. The function's concave down if the rate of change is decreasing. Now with these two graphs here, both of these graphs, they have a positive rate of change. If we draw secant lines along the graphs, they would be uphill. Both of these are increasing graphs. But on the graph here on the left, if we go from, say, x is 0 to x is 1, we have a rate of change. But then as we go from x is 1 to x is 2, again, we still have a positive rate of change, but the length of the rate of change, the amount of increase, has gotten larger. And if we take another step from axis 2 to axis 3, we're getting an even greater rate of increase for a given interval on the x values. So here we have what we call a concave up function. The rate of change is increasing. The change in y is getting larger and larger for the same change in x. So this one would be what we call concave up. The graph is getting steeper as it increases. On the right here, this function also is increasing. As we look at it from left to right, it's going uphill. But as we go uphill, for a given value of x, the steps are getting smaller and smaller. We're still increasing, but we're increasing at a decreasing rate. And so this would be what we call concave down. One thing that I like to use when I'm looking at a graph to remember concave up and concave down. If a function is concave up, it could maybe hold water, versus if it's concave down, it would spill water. That might be a little easier to see on the next graph. Okay. This is a trigonometric graph called a sine graph. And for this one, we've got several points here that we can use to introduce some of our vocabulary. We can see on this interval here, the graph is increasing, and here the graph is decreasing, and then again the graph is increasing. So because we're changing here from increasing to decreasing, this red point here would be a local max. And then down here, where we're changing from the graph being decreasing to increasing, we have a local minimum. Okay, so those are all pretty intuitive. The newer vocabulary that's a little more subtle. Here, the graph is increasing at an increasing rate. Sorry. Here we're increasing at an decreasing rate, whereas here we're increasing at an increasing rate. So here the graph is getting steeper. So it's concave up. Back over here, the graph is increasing, but not getting steeper, getting more gradual. Less steep. Here the graph is concave down. Okay. Here also, continuing our green line, the graph is also concave down. It's going downhill, but the rate of change, the slope to that, is still down, still decreasing, until we get to this red point here, and that's where the concavity changes. So this red point here is what we call an inflection point. The concavities change there from being concave down to being concave up. Here, all along this interval here, the graph holds water, it cups it, so it's all concave up. Whereas along this part of the interval, the graph is concave down. And where the concavity changed is called the inflection point. All of these minimums, maximums, inflection points we'll be talking about in this class, and we'll be talking about them in even more detail when we get to calculus. Thank you.